A very similar chi-squared test to homogeneity is independence. It's slightly different here because we're asking a different question, whether two variables are independent. The null hypothesis is always that the variables are independent, and the alternate is that the variables are not independent. You could also say dependent, but I see this wording a little more often, and I like it a little better, even though it is stranger. So the way we test whether the variables are independent is whether the distributions are the same. The alternate hypothesis would be that the distributions are different. So the wording is different, but the math here is going to work out the same as the test of homogeneity. Let's go through a quick example. We survey 389 people about whether they use marijuana and whether they believe it should be legal. We want to know if use is independent of belief in legality. So we get our results and we'll put them in a table again. One of the worst looking tables I've ever made, but it will serve. This is information that always has to be provided for you unless you do your own research, in which case you have to come up with it yourself. So the first thing to do is just come up with the overall total. So our overall total is 28.3% of people believe it should be illegal, 71.7% believe it should be legal. So we're going to use this, similar to the previous one, to come up with expected counts for the whole table. The way we do that is we multiply this total percent by the row totals to get the expecteds for each of these. So 0.2828 times 318, 0.7172 times 318, 0.2828 times 71, and 0.7172 times 71. After we have expected counts, we do expected and observed, the same formula to come up with our chi-squared contributions. So that works out this way for here. Just doing the formula here, observed minus expected squared divided by expected. And then do the same thing for the avoid and the totals you're going to get. Add all of those contributions up to get the total chi-squared test statistic. The degrees of freedom, again, is number of rows minus 1 times number of columns minus 1, which in this case is 2 minus 1 times 2 minus 1 equals 1. To get the p-value, we'll go into GeoGebra again. In GeoGebra, we have the chi-squared distribution again. Degrees of freedom is now 1, and our test statistic, 8.365. We get a p-value of 0.0038, quite a small p-value indeed. This p-value is less than alpha, assuming 0.05 again, so that leads us to reject the null hypothesis. But of course, don't just leave it there. Put what that means in the context of this situation. We started off by saying the null hypothesis is they're independent, so say they are not independent. Instead of saying the variables, just say what the variables are. Belief in legalization of marijuana is not independent of use of marijuana. And even though I made these numbers up, I think this would be the conclusion you would find, because people who use marijuana probably have a little more vested interest in wanting it legalized. Of course, I made up this example years ago, and things have changed a lot since then, so who knows where it is now. This illustrates something that might help you understand independence. If I just look at this same data we started with, but I present it in row percent form, 80 over 318, 238 over 318, 30 over 71, 41 over 71 here. I can just see that the percentages here are very different. Only 25% of people who use it think it should be illegal, whereas 42% of people who avoid it think it should be illegal. So the distributions aren't really the same when you put them in terms of the overall number of percent, which is why we end up rejecting the null hypothesis. If the percentages here and here were very close and these two were very close, we would probably fail to reject it.